Hi, my name is Adit Sharma, and my senior project title is Application of GANs to Image Tiling. So, what is image tiling? Um, well, one place you might have seen it is in old 8-bit video games. In the early age of game development, space, memory was a huge limiting factor. And so, what game developers did was they would have a small set of images called the tile set. And from this set of images, they would render the game backgrounds, all the scenery and the background. So if you look at this picture over here, you can see, oh, there's a grass tile, there's a pink flower tile, there's a blue flower tile, there's water tile, and you could create an entire background from a small set of tiles. So Outward Inc. This is my external advisor for my project. I had an internship there the summer after junior year, and they were founded in 2012. They were a 3D AR VR startup, and in 2017 they were acquired by Williams Sonoma. And what they do is they power Williams Sonoma's interactive room planner. Here. Okay, so image tiling in outwards context. Well, let's talk about the room planner. So what the room planner lets you do is it lets people who are buying furniture from Williams Sonoma try out different pieces of furniture, like different rugs, different couches, different pillows, different pottery, and they lets them try that out in real time. It's a 3D tool, so they can pan around, get different angles of their room, play around with different textures. For example, this rug, maybe a polka dot rug or something like that, but it lets consumers basically whatever they would be doing in real life, they can do it online in seconds. So why is image tiling necessary? Well, something about this interactive room planner is it is a 3D augmented reality, virtual reality type of software, and that we want to be rendering textures onto 3D objects with great precision. So in the process of rendering textures onto 3D objects, you want the source textures to be matching the size of those objects in real life. We can't simply, uh, for example, take this rug. It might take up a few inches on your screen, but we can't just take a few inches, like maybe suppose this rug is 10 feet by 8 feet in real life. On your screen, maybe it's 4 inches by 3 inches. We can't simply take a 4 inch by 3 inch image of that rug and render it onto the object. What we have to do is we want to take the full 10 foot by 8 foot rug, which would, is around 12,000 or 14,000 pixels, and render that full texture onto the rug to preserve the resolution, the high details, and to make it a realistic 3D rendering. So, unfortunately, though, rendering huge textures in the range of tens of thousands of pixels is extremely slow, relatively. It might take at least 10 seconds or more. And with the interactive room planner, consumers don't want to have a huge lag between, clicking on something and seeing it before then. We want the latency to be uh, under a second for sure. And so what Outward does is instead of rendering one large texture onto these furnitures, we can instead take a small image, maybe instead of 12,000 pixels, only 400 pixels, and use parallel processing, whether that be GPUs or other computers, or a application-specific integrated circuit, um, and tile those at the same time. So instead of tiling, having to go through one huge image, we can we can split the work and just tile 400 pixels at a time, which is extremely fast. But there are additional considerations that need to be taken. So tiling artifacts, and artifact is an unintended consequence of something. So suppose we have a green square, perfect image for tiling. We can easily tile this, just repeatedly paste the image next to each other. And you can get this, here, let me go back. There was supposed to be an animation. So we can repeatedly paste it and we get this bigger image. It looks basically the exact same as the original image. So perfectly tileable. But take any real world image and you might see, oh, look, here there's a tiny, tiny gradient from right to left. Maybe because the sun was at the right side when the picture was taken, or that's just natural variation. To add more natural variation, suppose there's a black dot in your thing. But it doesn't have to be a black dot. It could be any sort of feature, maybe a particular, like an odd square in the carpet pattern or something like that. But any sort of feature that stands out takes away from the homogeneity of the picture. Well, when we tile this, you can see a clear seam, and that's because of that gradient. And you can also see this dot is appearing multiple times. So this tiled image clearly does not look like a scaled up version of the original image. It looks very obviously that you took this image and you just copy pasted it to a 2x2 grid, but we don't get that seamless tiling effect that is extremely important. And basically what the goal of my project is to see how we can go from a raw image, just a raw image in the real world that would not be tileable, to a tileable texture. How could we transform this? So let's talk about generative adversarial neural network. Here's a picture to illustrate what it is. Basically, it's two neural networks that are working against each other to sort of converge to a solution. So another way to describe it is it's basically a neural network where you're learning the cost function while you're also learning the generative function at the same time. But you don't have to explicitly provide a cost function. That's the role served by the discriminator here. So let's talk about how it works. Basically, you have two networks, a generator and a discriminator. And the generator is trying to generate samples, and the discriminator is fed both samples from the generator and real samples. And its job is to distinguish or classify them. So loss formulation is basically, you want the discriminator to classify real samples as real and fake samples as fake, and the generator's loss is the opposite of whatever the discriminator's prediction is. So if the generator wants the discriminator to classify its output as real. It wants to fool the discriminator. So this is the basic framework of a GAN. GANs are actually, unlike something like what you might be more familiar with, GANs don't actually learn a mapping. Rather than learning how to map from A to B, the concept is it maps from the domain of A to the domain of B. So if you look at this picture here, you're just feeding the generator a latent random variable. So here the generator is taking an input from a random distribution, and it's mapping a random distribution, the whole distribution, to whatever this real world image distribution is. So something about generative models, unsupervised learning in particular, is it tends to not be simply learning mappings between samples, between training data cases, but rather across whole distributions. One key feature about unsupervised learning is that you're not trying to learn this mapping, you're trying to learn some underlying feature that connects two data sets. So for my project, after considerable research, I found the optimal GAN framework because, like I said, the last slide, that was the basic GAN, but there are improvements to make on it, or changes, modifications, tweaks. So I settled on using a conditional GAN, which instead of just feeding your generator random noise, you also want to feed it some input to condition its output, hence the name. Now, you still want to feed it this random variable because ideally you are not trying to learn a mapping from y prime to x. You do want to learn the mapping from the domain of y prime to the domain of x prime. However, so in the original paper that came up with the conditional GAN, they introduced this random noise to try to mitigate the generator from learning just a mapping. As of right now, it's an open question, as the authors have left it, in that the network does more or less learn a mapping, but I think the value of the GAN still remains in that when we're trying to go from images of type A to type B, we don't know exactly what the cost function is. If we just do, for example, a simple cost function like the square of the difference between the pixels, then you'll get really blurry results because that's what minimizes the cost function. Whereas in the GAN, you don't have to specify a cost function that you don't know what is optimal. And it actually learns the optimal cost function for you. So conditional GAN is what I ended up settling on, and for that reason, basically. Here's the picture of some code. I thought it would be nice to include. I spent a lot of time actually setting up, or not a lot of time, but I spent a day or two setting up my data pipeline, as I have seen it called online. Like figuring out how to go from the images, which my external advisor just gave me a link to a Dropbox with 100 gigs of images and told me that there's my data. So I had to figure out how to go from there to loading images. Well, one, getting them on my computer. Then I had to figure out how to load them into the TensorFlow dataset object, which is very convenient. It allows you to, it supports built-in functions like shuffling, batching. You can map every element of your data set to some other thing with custom defined. You can define a map function. It supports a lot of built-in features. So it was very important that I could get my data into that object so I could have all these, have all this functionality. So figuring out how to parse this into that was a undertaking of its own. So next slide, results. So I think you can actually look at my week 10 blog post for some images. And the way these images are ordered is the first image you see is the input image. Second image is the ground truth, you know, what has already, like what we ideally want it to be. And the third image is the predicted image. And then the second set of three is just tiled to 4x4, a 4x4 tiling of the same images. So if we see, the model has learned to recreate these patterns relatively well. Like here, it's created this bullseye pattern pretty well. Here, it's created this zigzag pattern pretty well. However, if you look at these white parts, for example, here these white bands or these orange bands, there's a lot of noise, um, which is something I noticed, and I think that can be explained by, well, low-level convolutional filters are responsible for generating these, low-level patterns, and then since we also have images such as, like for example, this or this or this, where there's a very intricate high frequency pattern, those high level convolutional filters have uh, obviously learned to do something. That's how they're able to create these high level patterns. But in the absence of any sort of high level patterns to create, uh, I think those high level convolutional filters are just creating random noise. And I think that's the noise that you're seeing. Um, Due to time constraints, I don't think I can really test this theory out, but I think it's relatively straightforward way to explain the noise. And as you can see, these images are very much so tileable, these generated images, whether that's because it just learned how to mimic the ground truth. And so it didn't really learn how to make them tileable, rather it just learned how to um, map to the ground truth. And since the ground truth is tileable, its prediction is tileable. Uh, Whether or not that's the case, again, there's not enough time for me to test. It's something that I'll definitely be working on my own time after the scope of this, outside of the scope of this project. But um, these are my results as they stand for right now. Um, and I'd be happy to answer any questions. Thanks for your time.